begin to start. So in 7.4, what we're going to do is we're going to take a look at equations that, although not necessarily are obvious that they're quadratic in nature, do follow some sort of quadratic form. And what we're going to see here is we're going to... Where did I put this thing? It's brand new. I just put it on. I lost 2 already. This is terrible. You gotta be kidding me. Alright. Anyone have an extra stylus by any chance in their bag so I can write? You got to be joking. You have an extra one? Ah, awesome. You have one too? Whoever's first, sorry. Thank you. I'll give it back. Remind me, please, again, to give it back to me. Alright. So what we're doing in 7.4 is we're taking a look at equations that are in quadratic form that may not be necessarily obvious. So we're going to recognize the quadratic nature of the equation and solve it as a quadratic, even though it doesn't necessarily look like a quadratic. Okay, even though it doesn't look like one. Alright, so let's take a look at this first example of what I'm getting at. Obviously, the first equation is very easy to solve. Not only is it easy to solve, but it's also factorable. I could factor the first equation into x plus 5, x minus 2. So the first one is really easy to solve. What do you notice about the next two? What do you notice about the next two equations? And obviously you're comparing them. Yeah? Okay, you have to distribute something. That is something that's true. But look at that and compare it to the first equation.
X is substituted for 2x plus 4.
Yeah, it's the same thing, really. This 2x plus 4 right here, and this 2x plus 4 right here, takes the place of that x and that x right there. Same thing here. 2 over x takes the place of that x right there and that x right there. So these second two equations, although it looks like you want to distribute and FOIL it out, and like for example number 2, go through a whole process, you don't have to. You could write the second equation like the first one and solve it actually. Okay, we're going to talk about something where we, remember earlier, it was about a unit ago or two, I gave you an idea and I said let u equal something. It might make it easier if you let u equal some expression. We're going to do that here with this topic. Okay, we're going to do exactly that. Look at this first example and see what I'm getting at here. Okay, let's see what I'm getting at. So if I look at this and I recognize right away that I've got something squared, I've got something linear, and then I've got a constant, I can see that this actually is a quadratic. I'm going to move the 21 over first. And then somebody tell me a quadratic that would look like this, but it's a lot easier to solve. What would the general quadratic look like? That would be a lot easier to solve. Jeff?
1 squared minus 4y minus 21.
Yeah. Okay, any variable, doesn't matter, yeah. Okay? Something squared minus 4 times that something minus 21. That's literally what that looks like. Well, the only way I can write that is if I actually use a let statement prior to that line and say simply, let u equal 2x plus 1. Let u equal 2x plus 1. Now, if I solve this equation here for u, I can then take those numbers and plug them into the let statement to solve for x. Because our goal is to get x, not u, but we can get u first, and then using the values of u and the chain rule or the substitution property of equality, we could substitute our answers for u into the let statement itself. So what do you get when you factor this? What do you get when you factor this? X minus 7, x plus 3, and it's u, sorry. I'm only emphasizing it because the x is above. And as a result, u equals 7 and u equals negative 3. So that is definitely the solution to the equation with u in it. But we are looking for x. So since these are the values of u, you're going to take them and plug them into the let statement separately and solve for x. No, so what happens is we have to when solving this, set...
Yep, never mind, sorry.
It's all right. Set of each equal to 0 and solve. So what we're going to do is we're going to take this 7 over here, and we're going to set it equal to our let statement. Right here. Okay, so what I'm doing again is I'm taking this right here, and I'm substituting my answer back in for u so that I can get x. Because I've solved for u. There's the value of u right there and right there. So take it and plug it in right there, and that's what it'll look like on this side. Now on the right-hand side, I'm going to have negative 3 equals 2x plus 1. But in both statements, I'm realizing that I'm solving for u and setting it equal to the let statement. Okay, so then go ahead and solve for x. On the left-hand side, I'll subtract 1 and divide by 2 to give me a 3. Okay, subtract 1, divide by 2. Over here, subtract 1, divide by 2, gives me negative 2. Now, if you wanted to check something like this, there are two ways to do it, obviously. You could literally just plug your answers back into the original and check. Okay, plugging them back in at the very top, in the original statement at the top up there, and checking. Now, you could also, if you really wanted to take more time, which is a waste of time, but you could if you wanted to, FOIL out the top, distribute the top, right? FOIL all this out, distribute the 4 to both terms, go through the process of collecting like terms, and then you would actually be able to factor and get your 2 integer solutions. But this takes more time to FOIL it out and collect terms, so we recognize that this is a quadratic in nature, although not written that way. This example is probably, like, I'd say half students I've encountered will just distribute it out and solve. Others will use the use statement. Another one we're going to do in a moment, though, it's very important to use a use statement. It makes it a lot easier than trying to multiply things out or do things like that. Okay? All right, let's take a look at the second one and see how different, but applying the same concept. Here's the problem here. It looks like this isn't a quadratic because we see that we don't have something squared. I don't have anything squared, so it does not seem like a quadratic. It does not seem like a quadratic at all. Anybody have any idea what I could do here? Alex?
You can square both sides and give it a square root, but you get a square.
Remember, the thing is this, I can't square individual terms. I could square things if they're underneath, or if they're as a product, like something like this, remember, Alex? I could square, right? But something like this, I can't just square both terms. I would have to FOIL it, wouldn't I? So I can't just square both sides. Good idea, though. I like the idea. He's trying to get to something squared, right? Other suggestions of what I can do?
Let u equal root x.
Let u equal root x. And let's go back to the previous one. Let's go back to the... We're going to see that the b value, what it's attached to, is what we're going to let u equal to, as Jeff mentioned. Okay, and you can see that in the previous example. So we'll let u equal radical x. Well, what does that do? That means that u squared is just what? X. Make sense of this, please? So we'll start first by letting u equal radical x. And then, if I look at this and square both sides, which I can do here, I could say, well, the square of u is just u squared. And the square of root x, well, that's just x. So where I see an x, I should put u squared in this equation at the top. And where I see a radical x, I should put a u. All right? Now, the idea, again, behind this is that, God bless you. If you attempted to solve this one, you're going to run into some issues because you're going to have to isolate the radical x, square both sides. It's going to be a quadratic on the other side, which is going to probably cause you to have an extraneous root somewhere. We'll test both of our roots. This method is so much easier because now it's a quadratic and you could just solve this. Okay, now, how would you go about solving this? How would you go about solving this? Yeah, and if you want to check if it's factorable, by the way, Is your discriminant a perfect square? That's how you can tell if it's factorable. Is the discriminant a perfect square? What is the discriminant here?
-7 plus, no, it's -7 squared plus 4 times 2 times 6.
Minus 4 times 6. But what does it come out to be? It comes out to be 1. The discriminant turns out to be 1 in this problem, which means it can be factored actually. So you can definitely use the quadratic formula. Always. Always, always, always. But if you want to test the discriminant first, and you notice if it's a perfect square, it means it can be factored. Okay? Again, if the discriminant is a perfect square, the quadratic can be factored. If the discriminant is a perfect square, it can be factored. So since it can be factored, I'm going to go ahead and factor it. I'm going to recognize that this has to be 2u and this has to be a u. Beyond that, I could have 6 and 1 or 3 and 2, both positive or both negative. I could sit here and try them out. Ideas? Anyone get the factors? Well, which -6 in the first spot?
Yeah.
And then -1 over here? That'll give us... Does it work? When I do inner, I'm going to get -6. Outer, -2. That gives me -8, doesn't it? I want -7 in the middle. It's got to be something else. Jeff?
2u minus 3 and times 1 u minus 9.
Let's take a look. Inner will give me -3. Outer will give me -4. -3 and -4 gives us this -7. Okay, because this is a negative, obviously we knew that these signs had to be negative. Because this is, or either they were opposites or they were both negative. Because this was positive, these signs both had to be the same anyway. So I'll get u equals 3/2 and u equals 2. So although my answers are fractions, or one of them is a fraction, it is clearly still rational, right? It is still rational. This is not an irrational solution. So if those are the values of u, what do I have to do again? What's the last step for these problems? If those are the values of u, what should I do with them? Well,
Plug it into what U stands for, so radicalized.
okay, so we have u gets plugged into whatever it stands for, which is the let statement. So let's plug it in right up there. So 3/2 equals radical x. Or 2 equals radical x. Remember, I take the values of u, as Will said, and plug it into the let statement. So what does x become? Remember, just square it to get rid of the square root. What does x become? Obviously, on the right-hand side, it's 4. On the left-hand side, we have 9/4. Do they both work? Do they both work? How do we know if these are both true answers? What do we do? Where? Yeah, take these and plug them in the original, please. Okay, up at the top. Let's take a look, see if these work. Why am I testing this to see if it works for sure? Anyone know? Why am I testing this? In the last one I didn't test it. I kind of assumed it was true. Why in this one? I'm going to test 9/4 first. Why in this one am I testing it? Nobody who knows? Think back to chapter 6. No? In chapter 6 we talked about this. We talked about how when you solve something with a square root, there's a good chance that sometimes you have extraneous solutions. So whenever you solve something with a square root involved and you get two answers, one of them may be extraneous. Okay, and remember that when you're evaluating, you always look at the principal root here. So 2 times 9/4 is going to be 18/4 minus 7. Now, radical 9/4 is going to be 3/2 plus 6 equals 0. 18/4 minus 21/2 plus 6 equals 0. Common denominator. I could multiply through or just find a common denominator. I'll make this 42/4 18/4, and 24/4. 18 and 24 is going to give me 42. So I'll have positive 42, negative 42. We'll get 0 equals 0. That is true. And then we have to check the number 2 as well. Or no, what was the other answer? 4? 4. Okay, checking 4, we're going to get the following. Let's see, we have 2 times 4 minus 7 times root 4 plus 6 equals 0. 7 times root 4 is going to be just 14. So this also does work. Okay, but please check your answers that involve square roots. Check your answers that involve square roots. This is going to be 14 minus 14. Let's see. I want you to try the third one on your own. Take a look at the third one. I want to get an idea of who thinks they know what we should do to start. It's a little bit trickier, this one. Be careful, please. Careful. I gave you a rule that said, usually whatever B is, you should let that value become, your use statement and stuff. But here we have to kind of tweak that a little bit. Can anybody see what I have to do here? For example, if I let u equal 6 over x, that's not going to work very well because I don't see 6 over x inside of the square. Right? Again, I don't see 6 over x in here, so I can't let this equal u. It's not going to work. What should I do? There's a simple yet beautiful solution to this. Jeff?
Could you take, could you let u equal 1 over x?
You could do 1 over x. That works also. I wasn't thinking that, but you could do that. If you did that, what Jeff is saying is he's saying this. He would take the 3 square down, put the 9 in front, and then write this as 1 over x squared, right? And then he would say, okay, this is going to be 6 times 1 over x minus 35 equals 0. Everybody see how that works? Again, this 3 squared is really a 9. He's going to bring the 9 out, write that as 1 over x. This is 6 times 1 over x minus 35. That works. There's an easier thing to do, though, for this one. That works, though, Jeff. You could definitely solve and it would work. What could I do that might be a little simpler? How do 6 over x and 3 over x differ? How do 6 over x and 3 over x differ? And give me a factor of increase.
Well, 6 over x is 3 over x times 2.
Exactly. 6 over x is really 3 over x times 2. So we should write 6 over x as 2 times the quantity 3 over x. So let's replace this with a statement saying the following. So we'll leave the beginning alone. We'll write this as 2 times 3 over x. So Jeff, in the end, you see how it's the same thing, really? Okay, so either way works. Either of these work. But I would write it the second way just because it's easy to take out a 2 and then let 3 over x equal u. Okay, but it's the same thing, whether I use 1 over x or 3 over x for u. Okay, so I've written it this way now. So my next line says this. Let u equal 3 over x. Please, make that statement. I know it seems trivial. Seems like it's extra work, but making that statement reminds you at the end to go back and plug in for u. So the equation becomes, again, this is u right here. This is u right here. So replace wherever you see 3 over x with a u. And that's what the equation becomes. Again, just look, you see the u in red here. That's just replacing 3 over x. I can do that because of this let statement. If I say that u is 3 over x, this is just a property of equality, or a substitution property of equality. I can plug this in both spots. I could substitute in for it. And then I think is this factorable? I think it is. It is, right? Yeah. U plus 7, u minus 5. There are my solutions. My solutions to the equation written in u. I want the answer for x. James, what should I do with these answers now?
On the back.
To what? Not the original, be careful. Remember, I want to get x, James. I have u. Because if I plug them in the original, I'd be checking the answers for x, right? But I want to get x still. I want to get x still. Where else do you see x on the page? Look up at the board. Where else do you see x? Yeah. So let's take the u statements, right, that we just solved for, and plug them in here to get x. Take the negative 7, plug it in there. You get negative 7 equals 3 over x. Take the 5 and plug it in there. You get 5 equals 3 over x. These two solutions on the right-hand side here, we have to go ahead and just switch. Remember how to do this? Multiply by x, divide by 5. Multiply by x, divide by negative 7. Okay, so on the bottom it's an easy answer. X is just 3/5. At the top, x is going to be negative 3/7. Okay, again, how do you ever solve something when it's in the denominator? Multiply by it and then divide by this side. So literally just switch these two always. Okay, negative 3/7 and 3/5. For the sake of time, I'm going to tell you that these do work because the check would be very, not difficult, but lengthy. Go back to the original and think about this. You would be taking a fraction and plugging it into a denominator here. So it can get a little bit messy checking this. All right, it can get a little bit messy. Just go through your simple arithmetic for it. All right, example for yourself. You might be able to just solve this. A lot of you have done these before without even using the U statement. But think about a U statement here to help you. Think about what the U statement could be in this case to help you. And obviously remember that it's got to equal 0 to do this. It's got to equal 0. So you can go through this process, but I know some of you realize right away that this numerator, this original part here at the top, can be factored with x squared and x squared. If you do it that way, that's fine. You don't have to use U substitution here if you don't want to. Okay, so if you wanted to just start by factoring at the top, the problem you're going to run into, okay, let's see, in this case, well, it won't be a problem. You just have to remember to go further. Okay, factoring it like this works also. Recognizing that this should be a plus 4 and a minus 3. Okay, that works. You could do that. Or you can go down to this line, but it's going to be the same thing. So if we solve the u equation or the x equation, we'll end up getting the same thing, obviously. Because we'd have to take these values now, for u equals negative 4 and u equals 3, and plug them in here to get what x is. Or we can go ahead and continue to solve this. Depending on which way you do it, you get the same answer, but I think one is more direct than the other. Go ahead and solve this one at the top. You're going to have x squared plus 4, set it equal to 0. Right? For solving this right here, set x squared plus 4 equal to 0 and solve. Set x squared minus 3 equal to 0 and solve. That works. Or take these answers we got a moment ago and plug them in here for you. Okay, I'm showing the u solution at the bottom. If you want to continue the one at the top, you can. So if I set those each equal to x squared, because remember u was defined as x squared right here. If I set them each equal, I'm going to see that x is going to be plus or minus root 3. And then x is going to be plus or minus 2i. Why did I get 4 answers to this? Plus or minus, plus or minus. Why did I get 4 answers? What's the reasoning for that?
Because, it was x to the fourth in the original equation.
Yeah, the original was x to the 4th. The 4 indicates you're going to get 4 roots, of which 2 are imaginary and 2 are real. The 2 real ones, plus or minus radical 3, happen to be irrational, whatever, but the other 2 happen to be imaginary. But still, you get 4 answers. If you had solved those 2 equations at the top, if you went about solving these and you set x squared plus 4 equal to 0 and x squared minus 3 equal to 0, if you go ahead and solve those 2, you'll get the exact same answers. This will lead you to these answers, and this one will lead you to these answers down here. Okay, but again, I would probably let u equal x squared, and you have a simpler statement. This is the value of u. Plug it back in right here for x squared, giving you these 2 statements over here on the right. Hey, the last one for the day. The last one I want to get through. This is a more difficult problem. Suggestions? Any idea on this? If I think of the 19, I'm going to give you a quick hint. I need 2x minus 3 somehow, because I can't alter that. If I think of the 19 and I write it like this, plus 10x minus 15 minus 4 equals 0, I could see here that I could factor out a 5, and this becomes 2x minus 3. Okay, take a look at this tonight if you have time, please, just to get an idea of a different kind of equation, but still the same process. Prob said due tomorrow, review tomorrow. This homework is due Monday, your test is Monday. Practice test is on your documents and handouts. Yes?